Alright, hi students. Welcome to this online video where you'll be learning about the chapter on the rate of reaction, chapter 17. Right, specifically this video will actually focus on what we term as the factors affecting the rate of reaction, which is actually from your notes page 5 onwards, 17.2. Right, so without further ado, let's get started. Right, so in this chapter itself, before we can really talk about the factors that are affecting rate of reaction, we need to understand about this concept called effective collision. Right, so what exactly is the meaning of an effective collision? Now, an effective collision refers to the condition whereby the reactant particles are actually colliding with each other in the correct orientation. That means they are hitting in a specific manner. And very important is that they must have enough energy. So if you recall in the previous chapter on energy changes, we learned about this concept called activation energy. So all particles, they must have enough energy, or we term as activation energy, in order for the collision to be what we term as an effective collision. So two things: number one, they must collide with the correct orientation, and number two, they must collide with enough energy, or to have at least the activation energy. Yeah, so these two conditions will then allow what we term as effective collision to happen. Now, so what's the importance about effective collision? Now, effective collision is basically the one that allows a reaction to take place. Now, before any reaction can take place, we don't just look at collision between particles, it must be what we term as effective collision. So what this means is that, let's say, if you have two particles coming close to one another, they can hit against each other, that means they collide. But let's say they don't have the correct orientation, or they don't have sufficient energy, then they will actually bounce off one another, and then there's no reaction happening. Right, so I think this helps you to have a better understanding, but let's take a look at a video to visualize the process.
Reactions 1. In this video you are going to learn what is necessary for a reaction to take place. For a reaction to take place, the reacting particles must collide. But, just because they do collide, it doesn't mean they will react. Now consider a reaction between two diatomic molecules, AA and BB, to give two molecules of AB. This can be represented by the equation. These two diatomic molecules can collide in many different orientations, but consider the two orientations here. In orientation 1, the two diatomic molecules A2 and B2 are in the correct orientation to react. In orientation 2, they are not, and so no reaction occurs. Imagine our reaction being that of a ball of yellow plasticine reacting with a ball of red plasticine to give just one ball consisting of the yellow and red plasticine stuck together. If you slowly roll the ball of yellow plasticine towards the ball of red plasticine, they will collide. However, if you pick up the ball of yellow plasticine, the ball of red plasticine will not be stuck to it. No reaction. If you throw the ball of yellow plasticine at the ball of red plasticine, again they will collide. But this time, if you pick up the ball of yellow plasticine, the ball of red plasticine will be stuck to it. There has been a reaction. We call a collision that results in a reaction a fruitful collision. So, for the collision to be fruitful, the reacting particles must collide with sufficient energy. So to recap, for a reaction to occur, particles must collide with sufficient energy, and particles must be in the correct orientation.
Alright, so as mentioned in this video itself, right, in order for an effective collision to happen, there must be correct orientation, and there must be what we term as activation energy. I just want to correct what the video has mentioned just now about this term called fruitful collision. Now, we don't call it fruitful collision, so we use the term effective collision, right? So there's this is the fixed term that we have to standardize to use. Yep, right, so then let's take a look at the factors that's affecting the rate of reaction. So in total, there's actually 5 factors, right? So this should be written out in your notes. The first of which is what we call the concentration of the reactants. The second one is when only if you're looking at gaseous chemicals, right? So if you're looking at gaseous reactants, then the pressure can also affect the rate of reaction. So you might want to take note that this is only for gaseous. The third one is the particle size, or what we term as the exposed surface area of the reactants. That means how big the reactant particles are like. So for instance, are we comparing a powder form versus a chunky solid reactant, right? So are we using small powders or are we using a big chunk of the solid particles? The fourth one is the temperature, right? I think this one should be quite straightforward. And the last but not least is what we call the catalyst. Now, just to highlight over here is that when we talk about all these 5 factors, right, as a student taking pure chemistry, it's important to know how to describe how the particles behave and how this will lead to an effective collision, right? So it's not just about, oh, higher concentration means the rate of reaction is faster, full stop, right? So as upper secondary school students, we have to explain how the particles behave and how they lead to the change in the rate of reaction. Right, so to understand this concept before we go into the notes, right, I thought the next video will actually be a very good summary of what's going on. So let's take a look at the next video.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing two particles together and orienting them correctly in space so that the two can meet at the correct configuration and allow a reaction to take place. So, to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
Right, so as shown in the video, I think it brings across a very interesting point of view about how you can use a simple analogy to understand how effective collision actually happens. So let's first talk about the first factor on concentration. Right, as shown in the video just now, when the concentration of a solution increases, there are actually now more particles in occupying a given volume. This means, for instance, like when they say about how the room actually becomes smaller, right? So you actually now have a smaller volume of space given, but there's more particles inside. So this works like concentration. So for instance, right, if you think about it, when you see a concentration of 1 mole per dm cube, this means that there is 1 mole of particles in 1 dm cube of solution, versus something like 10 mole per dm cube. This actually means that there's 10 mole of particles in the same volume, which is 1 dm cube. So actually it increased by 10 times more of particles. Now what's so good about this is that it then increases the frequency of collision. Now look at the term over here. What we're trying to say is that this time around, the chances of the particles hitting against each other actually increases. But does this mean that the rate of reaction will increase? Actually not. What really affects the rate of reaction is that now there is this higher frequency of effective collision. And this is the key idea that you must take note of. Right. So when you say higher frequency, right, why do we use the term frequency? Because this means the number of effective collisions per unit time. That means how many of such effective collision, right, we talked about this just now, actually happens within a particular amount of time. And this is what really drives the rate of reaction. So when you have a higher frequency of effective collision, your rate of reaction will actually increase. Now, when we understand about this concept of how concentration affects rate, now let's take a look at the graphing, right? How does the graph actually look like? Now, in the context of a graph, right, how we actually determine the rate of reaction actually depends a lot on the gradient, right? So the gradient of a graph actually allows us to see the rate of the reaction. So over here, you have two graphs being shown for you. One is graph 1, labeled with 1, and then there's a graph 2, labeled with 2. Right, so let's say you are using an experiment whereby you are changing the concentration of the acid, right? So then you'll get two sets of graph. Yeah. So based on these two sets of graph, you can actually tell which graph is actually faster than the other one by taking a look at their gradient. So gradient can be identified through a tangent, right? So imagine there's a tangent line for the first graph 1, at the starting point. Let's say this is the tangent, as compared to graph 2, whereby the tangent is over here. Right, just looking at the tangent itself, we can measure the gradient of the tangent, and we should be able to see that graph 2 is actually a much faster graph, right? So from this entire thing, we know that graph 2 has a steeper gradient, therefore it shows a faster rate of reaction. So what can we conclude? We know that there's different concentration. This would mean that graph 2 is actually the one that uses the higher concentration. Right, so just to reiterate the point, right, so graph 2 using a more concentrated acid actually results in a steeper gradient. But there's also two very interesting points when you look at the graph, which is that actually eventually, right, for both graphs, they actually slows down over time, and the graph actually becomes less steep over time. Right, you can see that there's this curve, right, which eventually allows it to stay at 100 cm3 of volume, right? So what is actually happening when the reaction is progressing is that the rate will actually start to slow down because the graph becomes less steep, right? And why does that happen? This takes place because actually over time, as the reaction happens, right, the concentration of the acid as well as the mole of the magnesium, that means the reactants, right, actually decreases. Right? So as the reaction happens, the amount of reactants actually decrease as they are reacting, so they will start to disappear, right? So over time, you realize that the reaction will get slower and slower, and that's just natural because eventually all the chemicals will be used up, right? And hence the graph will eventually plateau. Secondly, why is the volume of hydrogen collected in both cases the same? Why is it always 100 cm cubed? Now this has to do with the concept that you learned in Sec 3 about mole concept, right? And the reason is actually because for both experiments, right, even though you change the acid, the magnesium was actually the limiting reactant. Now if you recall in Sec 3, limiting reactant, what this means is that it actually controls the amount of product, right? So if the magnesium that has been used is constant, that means you didn't change it, even though you change the acid concentration, it can become faster or slower, but the amount of product doesn't change because you didn't touch the amount of the magnesium in this case. Yeah, so these are two very important questions to think about. Right? If you're unsure, we can review this when we come back to class. The second factor, pressure. Right, so how does pressure actually affect rate of reaction? Just want to highlight that this is only for gases, so please help us to write this down into your notes. So this doesn't affect reactions that involves solutions, that means solutions only, or reactions that involves solids only. Right, this is only for reactions that involves the gases as reactants. So actually for gases, right, changing the pressure is similar to changing its concentration. Now what this means is that at low pressure, what happens is that the particles are actually much more further apart. Right? So this can be seen as, like, for instance, a case whereby there is low concentration. Right? So it is something like this. It is not really low concentration, but it's similar to the concept that there is very few particles in a given volume because they are so far apart. By high pressure, when you press the container, when you compress it, what happens is the particles are now closer together. This will be similar to what we call like a case of a high concentration, because now they are actually crammed side by side with one another. Right, so you get this idea that actually when you talk about pressure, right, it's pretty similar to the concept of concentration, but it's only applying for gases because it does affect how far they are. So at high pressure, what happens is that because they are closer together, collisions become more frequently. But most importantly, it's because the frequency of effective collision actually increases. Right, so we see this term again. You keep seeing us phrase it in this manner: higher frequency of effective collision, therefore rate of reaction increases. Right, because that is the proper way to explain about how different factors actually affect the rate of reaction. Next, let's take a look at the third factor. Right, third factor is about particle size, which means how big or how small the reactants are. Right, this is usually for your solids, right? Because there's a certain volume that they have. So let's say that you have a solid reactant and you actually cut it into smaller pieces. What happens is that the total exposed surface area actually becomes greater. Now, the greater exposed surface area will actually increase the frequency of collision, because then the chances of the reactant particles hitting each other actually increases. If you take a look at this diagram here, you can see that let's say you have a big chunk of block. You actually slice it into smaller ones, then you end up with 4 smaller blocks of the solids. What happens now is that imagine the red arrows are actually the different reactants. They are trying to collide with the big blocks. But once you have actually sliced it into smaller ones, there's actually more chances for the red color arrows to happen, because there's more chances for the particles to collide now that the surface area actually increases, right? Likewise, when this happens, we say that there is now a higher frequency of effective collision, and therefore this actually increases the rate of reaction. Right, so you will realize that the concept to take note of over these few factors is that as a student, you must be able to describe how the particles are like, be it in terms of the exposed surface area, be it in terms of the number of particles per unit volume, etc. Okay? Well, at this point in time, you might feel that there's so many different factors. How do you explain this, and how do you really remember how the change in factors can actually affect the rate of reaction? And this is where we actually can link this back to some real life examples, our daily life, whereby we see certain things that's happening around us, and that actually allows us to have a better understanding of how these factors affect the rate of reaction. One very good one is about cooking, right? So for those of you who cook at home, you know that small pieces of food actually cook much faster than using a large chunk of meat or a large chunk of food. And that's precisely because of the larger total surface area that's being exposed, and that actually allows for a higher frequency of effective collision, and therefore the reaction can happen, and etc. etc. Right, so this is one good example. Another one which I think may be of interest to some of you right? Actually in places whereby there are coal mines, whereby there are actually miners that go in to dig for those resources, right? There can be a potential danger whereby there are actually what you call very fine coal particles that can actually ignite or explode very easily. So over here, this image was actually from an incident that happened in 2023, 28 October, whereby one of the coal mine actually went through a methane gas explosion, right? And that's because of how these small particles, right, can actually accumulate, and when they actually ignite or when they explode, the rate of reaction will be so fast because of the high exposed surface area. Therefore, the frequency of evacuation is higher, and then for the rate of reaction is faster, and that will give rise to an impact as great as what you see over here. Now, if you are interested to find out a bit more about combustible dust explosion, you can actually head on to this URL over here, which is also in the links, the YouTube links description box as well. It will introduce you to more about the science behind all this combustible dust explosion. A third example, right, if you have drank such vitamin tablets before, right, you would be better able to appreciate what's going on here.
How does size affect the speed of a reaction? Let's find out using an experiment that you can try at home. We will be using effervescent vitamin C tablets and water. As the tablet dissolves, a reaction occurs between aqueous citric acid and sodium hydrogen carbonate to produce sodium citrate, water, and carbon dioxide gas. To investigate the effect of particle size on the rate of a reaction, we will be using 2 glasses of water and 2 vitamin C tablets. One is a whole tablet and the other has been crushed to a powder. What do you expect to see when the tablet or the powder is added to the water? What do you observe? In both glasses, we see effervescence and the color of the solution changed from colorless to orange. We also observed that the rate of these reactions was different. In the glass to which the powder was added, the color change happened more quickly and the effervescence also stopped more quickly. Why do you think this happened? For the key reaction to occur, citric acid must first dissolve in water to form hydrogen ions. So let's focus on the reaction between citric acid and water. To simplify things a little, let's imagine that the whole tablet is made up only of citric acid. Let's zoom in to see the arrangement of the particles in the tablet and in the powder. How many citric acid molecules are exposed to water in the tablet and the powder? For the same number of molecules, more citric acid molecules are exposed to water in the powder than in the tablet. Another way of describing this is that for the same mass, the powder has greater surface area than the tablet. This means that the likelihood of a successful collision between the citric acid molecules and water molecules is more likely when the tablet has been crushed to a powder. To put it together, the powder has a greater surface area than the tablet. Since the powder has more particles exposed to water than the tablet, the likelihood of a successful collision, such as the one between water molecules and citric acid molecules, is higher. Thus, the powder dissolves more quickly compared to the tablet to form aqueous citric acid, and the subsequent reaction between aqueous citric acid and sodium hydrogen carbonate occurs and is completed more quickly. Hence, we observe the color change of the solution more quickly, and the effervescence stops more quickly. In conclusion, a decrease in particle size or an increase in surface area results in an increase in the speed of a reaction.
Alright, and I think as the video has very nicely summarized, right, how the decrease in particle size actually leads to an increase in exposed surface area, which then, as what we mentioned, leads to a higher frequency of effective collision, therefore increasing the rate of reaction. Yeah, so when you think about particle size and how it affects rate of reaction, no harm actually relating it to the day-to-day experiences that you have, and it might help you better understand the how the process actually works. Next, we have our fourth factor, which is on temperature. Now, I believe that when you talk about temperature and rate of reaction, I think all of you watching this video, you'll know that a higher temperature results in a higher rate of reaction, right? But like what I said at the start of the video, it's not so much about what is the connection between the factors and the rate of reaction. I think this one most of us will know, but what's more important is that how do you describe what actually happens? Now, when there's higher temperature, the particles of the reacting substance will actually gain energy. And when particles gain energy, they'll naturally move faster, right? This was actually also alluded to in the analogy just now, talking about the school whereby people are moving, right? Moving faster. Now, when they move faster, collisions become more frequently, and of course, our key phrase, there will now be a higher frequency of effective collision, and therefore the rate of reaction actually increases. And that is how temperature affects the rate of reaction. Right? So it's really more about how do you structure your answers to explain about the particles. A few examples to help us relate to it. So for instance, when you use your fridge, right, there's a freezer compartment. Now in the freezer compartment, the temperature is super low, right, negative 20 degrees Celsius or sometimes even lower. And the intent is actually to reduce the particles energy so that there will be actually a lower frequency of effective collision. So any form of decomposition or rotting process actually slows down. So the chemical reactions in the food is slowed down, and hence the food can be stored for a longer period of time before it turns bad. And an example can be seen over here in this video as well.
How does temperature affect the rate of a reaction? Let's find out using an experiment that you can try at home. We will be using the reaction of effervescent vitamin C tablets and water. As the tablet dissolves in water, a reaction occurs between aqueous citric acid and sodium hydrogen carbonate to form sodium citrate, water, and carbon dioxide gas. To investigate the effect of temperature on the rate of reaction, we will be using 2 tablets and 2 glasses of water. One glass contains hot water and the other glass contains cold water. What do you expect to see when we drop the tablets into the 2 glasses of water at different temperatures? What do you observe? In both glasses, we see that the color of the solution changed from colorless to orange and there was effervescence. We also observed that the rate of reaction is different. In the glass containing hot water, the color of the solution changed more quickly and the effervescence stopped more quickly. Why do you think this happened? For the key reaction to occur, citric acid must first dissolve in water and dissociate to form hydrogen ions. So let's focus on what happens between the citric acid and the water and start by looking at the water molecules. In the liquid state, water molecules are arranged close together and in a disorderly manner. The water molecules can slide over each other and move throughout the liquid. What's the difference between the arrangement and movement of water molecules in the glass of hot water and the glass of cold water? The water molecules in the glass of hot water have more kinetic energy and move more rapidly compared to the water molecules in the glass of cold water. Thus, the water molecules that are moving more rapidly collide more frequently and with greater energy. This means that the likelihood of a successful collision is greater. To put it together, when the temperature of the water is increased, the water molecules gain kinetic energy, move faster, and collide with each other more frequently. This increases the likelihood of a successful collision. Thus, the tablet dissolves more quickly in hot water than cold water, and the reaction between aqueous citric acid and sodium hydrogen carbonate occurs and is completed more quickly. Hence, we observe the color change of the solution more quickly, and the effervescence stops more quickly in the glass with hot water. In conclusion, an increase in temperature increases the rate of a reaction.
Right, once again, a very clear video, right? So basically, an increase in temperature increases the energy of the particles, and therefore this leads to a higher frequency of effective collision. Therefore, it leads to your higher rate of reaction. Yep. Right, so I think the third example is actually something that you would recall that during one of our practical, right, this year, we actually did an experiment whereby we tried to add hydrochloric acid with this chemical called sodium thiosulfate. And the process, there's actually a yellow precipitate of sulfur that slowly forms. This was the one that you added into a conical flask. You place the flask on top of a piece of paper and see how long it takes for the words on the paper to actually disappear from your sight, right? Because the solids are forming within. So this was an experiment that you have done before. But now let's put it into context in terms of how a change in temperature could affect the entire results that you're collecting. So this is how it looks like. You will be familiar with this. So for this particular one, actually what is being done here is that there's actually a marked cross that's on the paper, right? So basically, looking through the conical flask from the top, likewise, you will see to make sure that the cross actually disappears from your sight. Yeah. So in this particular experiment that we're describing over here, we add in 5 cm of dilute hydrochloric acid, and we start the stopwatch immediately to record the time taken. Right. So for this particular experiment, the mixture was swirled once. The intent is to give it a consistent swirling. Right. We mentioned about this before in class, because you don't want to end up swirling once for one experiment, then twice or more times for the other experiments. Then after this whole experiment is being repeated at different temperature. So as you could imagine, what this means is that you have a few set of data, and then we are going to compare how the change in temperature actually affects the time taken for the cross to disappear from view. So one way to look at how to process the results, right, is to plot it through a graph, right? So the graph that we have over here is how the change in time, right, depending on the temperature that was being used. So you can see that as the temperature goes from the lower temperature, 30, to a higher temperature, let's say 60, there's actually a change in terms of the time that's been taken for the cross to disappear. So basically what you see over here is that the time taken gets shorter. Right? So the higher the temperature over here, the shorter the time taken for the cross to disappear. And this is aligned to what we have learned, right? Because the high temperature, we know that this will actually, if I write it in point form, increase in kinetic energy of the particles, right? And when this happens, the particles will move around faster. And when they move around faster, collisions become more frequently, and then this actually increase in the what we call frequency of our effective collisions. Therefore, the rate should actually increase. So the time recorded will be shorter. Yeah, so that's the whole idea behind this particular experiment. Now, but this is in terms of measuring in time, right? But time is not the same as rate, yeah? Because I think we have mentioned before that time and rate are actually different concepts. In fact, they are inverse of one another. So how could you actually express your answer in terms of rate? That's when you actually have to use the one that we did in the practical by taking 1 divided by time. Right, so to see how the rate actually changes, we can actually plot now the values of 1 over t, or 1 over time. This is actually basically allowing us to know the rate of the reaction. Sorry. So as you can see from here, in this graph, as the rate changes, as the rate increases from, let's say, 0.01 to all the way to 0.07, based on how the temperature changes, right, you can see that as the temperature increases, the rate actually also increases. So this actually allows us to come up with the same conclusion as what we've seen previously. It's just a different way to plot a graph, but it's just to help you understand how you can actually convert from the time that's being recorded to actually derive the rate of the reaction. And that's done by using 1 over t, 1 over time. So with this, actually you can start to attempt the worksheet 17b from your workbook, right? Or you can also attempt the self-practice questions on the end of this particular notes. But before we go to that, let's talk about the last factor. The last factor that can affect the rate of reaction is actually about the use of catalyst, right? So for those of you who are not too sure what catalyst means, basically catalyst is a substance which can increase the rate of chemical reaction, but they remain chemically unchanged at the end of the reaction. So it's a new chemical that you introduce in, but its job is actually to speed up the reaction, but itself actually doesn't change at the end of the whole thing. So you can reuse it over and over again. Yeah. So one example is the reaction of hydrogen peroxide, whereby it can break down to form water and oxygen. And this reaction can actually be speed up by using a catalyst known as manganese 4 oxide. And in terms of formula, this will be MnO2. It's a black powder. So let's take a look at a video to see how the use of manganese 4 oxide can help to speed up the decomposition of hydrogen peroxide.
Here you can see Mr. Andauer adding a chemical called hydrogen peroxide to a large jar. Hydrogen peroxide has the chemical formula H2O2. It's a little bit like water, except water has the chemical formula H2O, so hydrogen peroxide has an extra oxygen atom in its compound. If left alone, hydrogen peroxide will slowly break down into water and oxygen. You can speed up this reaction by adding a catalyst. The name of the catalyst is called manganese dioxide, and here some has been added. Straight away you can see the hydrogen peroxide is starting to bubble. These bubbles are caused by oxygen gas being produced as the hydrogen peroxide breaks down. You can also see a white vapour being produced, which is the water. The reaction is exothermic, so it will get warm. Remember, The catalyst, manganese dioxide, is not being used up in this reaction. Instead, it's simply speeding up the rate at which hydrogen peroxide breaks down into water and oxygen.
As shown in the video itself, right, you notice that when the professor first poured in the hydrogen peroxide, right, what happens is that the hydrogen peroxide is actually supposed to go through the decomposition already, right? So this actually is a natural process that will happen to hydrogen peroxide. But if you look at it, it seems like nothing is happening. And that's how slow the reaction is. But once you start to add in in the video you mentioned manganese dioxide, but over here I'll just call it manganese 4 oxide. Once you end the catalyst, you notice that in terms of observation, right, you start to see all this bubbling, and that is when the decomposition process actually speeds up much faster. If you recall just now, I mentioned that the reaction is to break down the hydrogen peroxide into water and oxygen. And this oxygen will appear as what we call effervescence, right? So you see all the bubbling just now, that is from the oxygen. And once the catalyst comes in, you realize that it's uncontrollable. The rate just becomes so fast that it keeps on going on, right? So, and that is the power of a catalyst. And what was also mentioned in the video is that the catalyst will actually remain chemically unchanged. So at the end of the whole experiment, you can actually filter out the manganese 4 oxide. Maybe you can dry up and then you can reuse it for other experiments. So what are some characteristics of a catalyst? Now, for a reaction to be speed up using catalyst, only a small amount is required, right? And very importantly to take note that a catalyst can increase the rate but not the yield of the chemical reaction. In case you have forgotten what is yield, it means the percentage yield of the product that can be formed. Okay, so just take note that rate and yield are different concepts. Catalyst is selective in its action, so this means that a catalyst cannot catalyze all types of reaction. A specific type of reaction, let's say reaction A, can only be catalyzed by a catalyst A, for instance. Like just now, that particular reaction that you saw can only be catalyzed by manganese 4 oxide, but not the other catalyst. So each catalyst can work on different types of reaction. Each catalyst can only work on a specific type of reaction. Yeah, so in terms of linking back to the previous chapter on chapter 16, where we learned about the energy profile diagram, and this is the part that we do need to draw it into your own notes. How a catalyst helps the reaction to speed up is that it actually lowers what we call the activation energy. You know from this graph that this is what we call an exothermic energy profile diagram. And I think very clearly you can remember that there's this hump that we term it as the activation energy. So what a catalyst does is that it actually lowers the activation energy. So imagine it's a mountain, but the catalyst actually brings the mountain down. So you look at the green line now, because the activation energy is actually lower in terms of the amount, it actually helps the reaction to progress much faster than what we wanted, and then the frequency of effective collision will go up. Likewise, the reaction will increase. Right? So do take note that although the catalyst may look different, like just now in the example, you might look that the powder has changed, but actually all the chemical properties remain unchanged. So therefore, you can always reuse and reuse the catalyst. But what about this thing called enzymes? So if you read through your textbook for this chapter, you realize that there's this thing called enzyme, and you are not seeing it wrongly, because this is not just for biology, it's also needed for chemistry, right? So basically, what we need to know in chemistry is that enzymes are what we call biological catalysts. So these are catalysts that can be found within our body. It's usually found in the cells, in different kind of biological reactions that's happening in our body. They are essentially the same in terms of how you think of catalysts, how it works, just that they are made of proteins, very specific in their actions, and they actually can go through this process called denaturation, which is unique to enzymes. Right? And last but not least, they are also sensitive to pH changes. Right? So we'll talk more about this thing when we look at worksheet 17C, as well as when we revise the textbook. It will give you more information about how enzymes are like and how are they actually a type of catalyst. By the end of the day, the focus is the same. Enzymes, they will help to lower the activation energy. Oops. Right, and when you lower the activation energy, what happens is that you then allow for an increase in frequency of effective collision, and therefore the rate of reaction will then increase. Yeah, so this will be pretty similar to what we understand about the different factors. And with that, we have come to the end for this particular video. Now, do take some time to try out the self-practice questions in the notes itself. That will really help you to have a better grasp of how to interpret the different graphs and better understand how the different factors actually affect the rate of reaction. And last but not least, as you do your workbook, it will help you to better phrase your concept into the key terms that you should take note of. And with that, we have come to the end of this video.